Stanford University.
It's my pleasure to introduce Dr. Anthony Wagner to you this morning. He is an associate professor of psychology and neuroscience and director of the Stanford Memory Laboratory. Was there one here when you all were here? A memory laboratory? You probably had no reason to go there. He did his PhD at Stanford in 1997 and joined Stanford's faculty in 2003. Professor Wagner's research explores how the brain supports learning, memory, and executive function. His research has been recognized through a number of awards, including the American Psychological Association's Distinguished Scientific Award for Early Career Contribution in 2006, and an Alfred P. Sloan Research Fellowship in 2004. Please join me in welcoming Professor Anthony Wagner.
Thank you. I think this is on. Thank you. You can hear me in the back? Great. So it's actually great to see everybody here at this early hour. I teach an undergraduate course in the spring that starts at 9:30, and maybe it's a sort of a generational thing between the current sort of undergrads and maybe past generations. But at 9:30, the number of undergrads who say, this is the earliest class I've ever had here at Stanford, and I cannot believe you've scheduled it at 9:30. It surprises me. I can remember the 8 a.m. classes not always showing up as an undergrad, and so I appreciate your showing up at this early hour. What I'd like to do, I'd like this to be a dialogue. You know, I do have content, slide presentation that I may make it all the way through, but please stop me at any point along the way to ask questions or to comment. So what I'd like to do during our time together is sort of share a little bit of my excitement about both the power of our memory systems, but also sort of the frailties of our memory systems and the significant sort of consequences that we suffer when our systems go awry, when they're impaired in some way. In the course of having this conversation, I'd like to also highlight the way in which changes in cognitive science, psychological science, and neuroscience over the last 15 or 20 years, in fact, changes that occurred really in the second or third year of my graduate training here at Stanford in the mid-90s, how these changes have kind of revolutionized how we approach trying to understand how the brain supports and the mind supports different forms of learning and memory. These changes both have an impact on our understanding of sort of basic processes, but also these changes are bringing potential sort of societal interface or interplay between basic science and applied science, perhaps in the courts and other settings. And I hope to end this presentation trying to sort of illustrate how my lab is beginning to wrestle with a thorny issue, or begin to think about a thorny issue, which is how modern brain imaging may or may not impact, say, the courtroom in terms of trying to assess people's cognitive states. Okay, so to start off my talk, and you'll forgive me if I trip over this cord 10 times during this talk. To start off my talk, I have this quote from Chuck Klosterman, who writes for ESPN.com Spin, and it's perhaps my favorite quote about the nature of memory, or about the centrality of memory for our cognitive lives. So Klosterman wrote, and he was actually commenting on the movie Memento, which is a fabulous movie. Most people consider forgetting stuff to be a normal part of living, and that in fact is true, and there's a wealth of data showing that in fact if we don't forget, there are negative consequences for ourselves cognitively, and we've done some recent work exploring the benefits of forgetting. That's traditional or sort of just standard healthy forgetting. Most people consider forgetting stuff to be a normal part of living. However, I see it as a huge problem. In a way, there's nothing I fear more. And here's my favorite quote. The strength of your memory dictates the size of your reality. That is, it is our long-term memory systems that allow us as cognitive entities to bridge and stretch the current brief temporal moment in our lives and really sort of stretch that temporal reality, bringing minutes, hours, days, years, or decades of knowledge from the past forward into the present to inform what we're currently thinking about, how we might what decisions we might arrive at, how we might act. And we actually see when you encounter an individual who's suffering from long-term memory deficit, their temporal reality is rather brief. And it's a really sort of disconcerting thing to observe in one's loved ones if you have a family member who's suffering from, say, Alzheimer's disease, where the kind of memory that I'll be talking about today is in essence shrinking that family member's or loved one's sort of temporal reality. But we became very, it was very stark, this sort of shrinking of temporal reality. It's very stark in individuals who suffer extensive damage to a particular part of the brain, a system called the medial temporal lobe. Medial because it's on the inner wall of the temporal lobe, and we'll be talking about this system for much of today. And this really came to our attention in the early to mid-1950s with a patient who became known to the field wide as HM. It's perhaps the single most important single case study, single neuropsychological patient in the history of memory research, perhaps in the history of cognitive neuroscience and psychological research as well. HM, as a young boy, 7 years old, had a bicycle accident. This resulted in him having a closed head injury. At the age of 16, he started having grand mal seizures, and they were occurring quite frequently and disrupting his life in a rather significant way. He lived with his grand mal seizures up until the age of 27, and unfortunately for HM, and this is the case for a modest percentage of individuals who suffer from epilepsy, his seizures could not be brought under control with standard anti-epileptic medications. And so at the time, he was a 27-year-old man now, and he and his parents decided that he would undergo an exploratory surgery with the hope of removing the part of his brain that was actually the site of his seizures. As it turns out, unfortunately, this structure we'll be talking about, the hippocampus, which is a key part of the medial temporal lobe, is often the site of temporal lobe epilepsy. And at the time, they didn't know whether it was HM's left or right hippocampus, left or right medial temporal lobe. And so they decided that they would resect or remove both hemispheres' medial temporal lobes. The hippocampus, which is sort of drawn here, it's like a seahorse, which is what where the name hippocampus comes from in the Greek. It's kind of lying on its back. And you can see in HM's brain, this is a scan of HM's brain in 1997, 45 years after his surgery, the dark areas where his hippocampus and the surrounding tissue in his medial temporal lobe should be sitting. And the surgeon, William Scoville, removed, again, the hippocampus and the surrounding structures in both hemispheres. And this was, in terms of HM's epilepsy, it was a successful surgery. It brought his epilepsy under control, and from that point on, 1953, until his death this past December 2008, he was able to sort of live relatively seizure-free using anti-epileptic medication. The striking thing, though, post-HM surgery was it became immediately apparent that from that moment on, HM, in essence, was frozen in time. HM was not able to form a single new conscious memory of a single life event that had occurred in his lifetime from that point, 1953, forward. The death of his parents, could not learn and remember that his parents had died, other significant life events. There were not, HM's brain, the loss of this neurobiological system prevented him from being able to form these new conscious memories of life's events. And this really revolutionized the field, transformed the field. At the time, there was a lot of work going on trying to see if there was a particular circuit or a structure in the brain in which memory traces lived. And there was some leading work by Carl Lashley and others doing lesion studies out in the rat's cortex and basically showing or suggesting that, well, no, there isn't a special sort of seat of memory in the brain. And shortly after Lashley's work, the observation of HM and other amnesic patients like him highlighted the centrality of this neural structure for the acquisition and later retrieval of conscious memories. So here's the amnesic syndrome that is often experienced by individuals who suffer extensive damage of the medial temporal lobe. And again, I'll quickly sort of highlight where those brain structures are in just a moment. So you've got time moving forward, and at some point there's some damage to the particular system. And the kind of memory deficit that HM suffered is Anterograde amnesia. That is the inability to remember events that have been experienced, memory for episodes, and facts. In fact, new semantic learning is also impaired following damage to the system after brain damage. So what you typically see, except for in the movie Memento and a few other movies, but what you typically see in terms of sort of TV and Hollywood dramatization of amnesia is there's some insult and the individual forgets who they are, they forget who they're married to, they don't know whether the person that they're interacting with is friend or foe, and yet they can move forward in time, remember new experiences. This is sort of the Bourne series, et cetera. And there's no problem with new learning, but it's sort of remembering the past that is the problem. That's not really what you see in organic, real-world amnesia. The real-world amnesia is there's some insult, and it's this inability to remember as you move forward. In addition, and we won't have time to discuss this, there also is some negative consequences for these older memories. And as you go further back in time, our older memories tend to be protected from or not impaired by the neural damage, whereas newer memories that were experienced and formed just prior to the injury are more likely to be the ones that are lost. But the principal impairment following medial temporal lobe damage is an anterograde amnesia. And this is, in fact, the principal impairment in most patients who have Alzheimer's disease, and you see this early on. The principal impairment you might, if you have loved ones, hear described as a short-term memory loss because it's a loss of the more recent things, memories for more recent things, as opposed to long-term memory loss for these memories further back in time. From a neuroscientist and a psychologist sort of point of view, it really is, it's a long-term memory impairment. It's an impairment in the ability to form new long-term memories for life events due to the change in the medial temporal lobe. Okay. Just to sort of give, for those of you who have not encountered anybody who has anterograde amnesia, give you a flavor of what the cognition is like. I have this clip of Larry Squire, Alan Alda, from the Scientific American PBS series, where it's a clip of patient EP, and patient EP has extensive damage to his hippocampus and surrounding structures in the medial temporal lobe and has a very frank anterograde amnesia. And this clip does a great job of sort of illustrating forms of cognition that are intact following medial temporal damage, as well as sort of the cognition that's impaired. So it's pretty striking sort of juxtaposition of intact cognition. Here's an individual who has intact visual spatial abilities. He can take, they didn't show it, but he can take a complex visual image and directly copy it. He can sort of keep in mind the instructions of what his task, what his goal state is, and he can accomplish that. He can carry on a conversation with the research team, with Alan Alda, and if that conversation is either significantly brief in terms of time, or it stays on the same topic for an extended period, he can seemingly sort of follow along and be engaged in the conversation. However, the moment that his attention shifts away from any particular information that he's holding in mind, that information just drifts away. It doesn't stick in his brain. He's not forming new long-term representations. And so whenever there are cues that might trigger thinking about that information, he can't bring it back to mind. He can report immediately after having a 4-item word list. He can immediately report them back. A few minutes later, there's those cues to try to remember that event because those memories were never built. Those cues don't unlock a memory, and he doesn't even remember even having the experience of seeing the list, let alone being able to bring the items back to mind. And in fact, these patients, as Squire notes, Sue Corkin, who interacted with HM for essentially 35 years, these patients never actually come to recognize the researchers that are often testing them for these over decades and have had hundreds, if not thousands, of interactions with them. Okay, so it's a rather striking juxtaposition of intact cognition for most other things other than long-term memory for new life events. Here's HM's sort of description in a very famous quote, his sort of concerns, his sort of conscious state. and his concerns about his conscious state. Right now I'm wondering, what have I done? Have I done or said anything amiss? You see, at this moment, everything looks clear to me. That is, at this moment, I understand the very local temporal sort of period in my life. But what happened just before? That's what worries me. It's like waking from a dream I just don't remember, right? And for those of you who haven't seen Memento, if you ultimately go and see it or rent it, it's this quote that I like to keep in mind, because in essence, the director, Christopher Nolan, is trying to place the audience into this state. And the movie, for those who haven't seen it, sort of runs in reverse chronological order. And what that does is it places the audience into a situation where they have no idea how they got there. It's like the audience has just woken from a dream and is trying to figure out, how is it that I'm here and what are we doing? In contrast to HM, we can figure it out in the course of the movie because we can build new long-term memories and we can integrate over the events that we're seeing. Unfortunately, for patients who have anterograde amnesia, that's unfortunately not possible, and life is highly fragmented into very brief periods of time. Okay. The clip of EP, as well as this quote from HM, makes one distinction very clear. That is that there are different kinds of memories, what we might think of as working memory, that is knowledge that is currently in an active state. What we now think of it as is it's the focus of our current attention. So the current focus of attention, that knowledge can stay in an active state independent of the medial temporal lobe. And so you can carry on an interaction with such an individual because they can keep information in mind for a brief period of time. When attention shifts away, then that knowledge, if there's extensive medial temporal lobe damage, again is lost, and it's as if that experience hasn't happened. And this can be contrasted, these sort of active memory representations can be contrasted with long-term representations for episodes, memory for individual life experiences, as well as long-term knowledge that's built up over numerous life experiences, what we think of as semantic memory, knowledge for facts and concepts. And these are durable changes, long-term changes in the system. We're going to be focusing principally on episodic memory here. So here are some of our discussion points for the remaining sort of 35, 40 minutes or so together. So first, just a very brief sort of discussion of why the hippocampus is so central to our cognitive lives in terms of building these episodic traces. So the hippocampus, here's the sort of a cartoon of the human brain. Sitting up here is the frontal lobes, prefrontal cortex. The eyes, of course, sitting right below the frontal lobes. Parietal cortex, parietal lobes, occipital lobes, and then the temporal lobes. And what we're doing is we're looking through the temporal lobes into the inner wall. And this structure here is the hippocampus. And then there's cortical structures around this structure. Here's sort of one of the key take-home sort of points about why the hippocampus is so special. If we think about an experience, there are numerous features of that experience, numerous elements. There are sounds, there are sights, there are objects, there are positions of things in space, there's affective value, reward value. These features are all co-occurring, and they're in essence being processed. You don't have to have a modular view of the brain to know that they're in essence being processed by different circuits and different systems in cortex and in subcortical structures. Excuse me. The hippocampus is the site in which this knowledge comes together. In essence, the hippocampus is at the apex of the information flow hierarchy, where the outputs of cortical regions throughout the brain are projecting ultimately onto the hippocampus. And the structure of the hippocampus, in particular layers in the hippocampus, also uniquely positions it to glue together, to bind the co-occurring information. The cortex can't do this. The connections between different cortical regions are relatively weak, and their rate of learning is very slow. In contrast, the rate of learning in the hippocampus is extremely rapid, and it affords one shot, one trial learning that binds together these different elements into a unified memory. Okay? And in a highly sort of simplified cartoon form, you can kind of here's sort of an example. Imagine you go to the homecoming game tomorrow. You're having some experience at this game. There's sounds, perhaps, of the band. There's all kinds of visual inputs. Parts of the brain process sort of sound inputs, both at lower levels of representation and then further in the brain up to higher levels of representation. Same with sort of visual inputs. These visual inputs at the low level sort of features ultimately get coded as sort of objects and spatial information and where these objects are occurring in space, where the sounds are occurring in space. You might have some positive affect and reward value, perhaps Stanford wins. All of these things are co-occurring and are essentially these different aspects of your experience are being processed in different parts of the cortex and subcortical structures. In addition, our frontal lobes, each of you is viewing the game with a different set of goals, a different set of sort of past history. And our frontal lobes are, in essence, by representing our current sort of goals, plans, agendas, are biasing which of these aspects of our experience is actually being attended, and in essence, which neuronal representation is sort of being facilitated. This dynamic interplay ultimately is funneling information, or results in the funneling of information into the hippocampus in the medial temporal lobe. And it's the architecture, and this ultimately results in multiple hippocampal neurons sort of firing due to the different inputs into the hippocampus. And it's the structure of the hippocampus and these neurons that when they're co-firing, they could rapidly wire together. They could rapidly associate with each other. And it's this remarkably reduced representation of all of this information out in cortex that is, in essence, the seat of our episodic memories. This associative structure is what holds together all of those event elements into a coherent whole and allows us to ultimately, at some point in the future, bring back that experience. If you don't have this representation in the hippocampus, you will not be able to consciously remember that experience. And these representations are critically, they're flexible. We can, at some point in the future, have some other experience, and there will be cues in that experience that might trigger remembrance of this past event. So imagine a few weeks from now, you're watching another Stanford football game on the TV. They happen to show a picture of the tree. Well, that may unlock this hippocampal representation from homecoming, pattern complete it in the hippocampus, and then reinstate the patterns of activation that were present in your cortex during that experience, and in essence, bring those details back to mind. And in a very simplified form, this is sort of how we think episodic remembrance sort of plays out or occurs in the brain. Yes?
So there's chemistry that is happening in that affective state. When that is retrieved, does the memory of your long-lost boyfriend give you the endorphin? Does that post-traumatic stress re-give you the cortisol? Is there chemistry tied with it?
So there's a whole host of neurochemical experiences that are going to sort of be occurring during remembering. Let me give you a systems rather than a chemistry sort of answer to your question. We have known for quite a while, there's this term or this phenomenon that I think we're all familiar with, this notion that we have flashbulb memories, that for really traumatic or meaningful life experiences, the brain, in essence, kind of sears it into that experience into itself, such that at some point in the future, it's brought back to mind much more vividly, much more accurately, kind of like bringing back a Polaroid, a photo in all its detail. We've known for quite a while from the psychological literature on memory that flashbulb memories aren't really flashbulb memories. These highly emotional, meaningful events like the assassination of JFK is a classic example, or more recently, the 9/11 disaster and sort of national trauma, that these memories are subject to forgetting through time. They're also subject to distortion, to errors. We know, in fact, people who claim, I'm certain that I remember that I learned about the assassination of JFK while being in my dorm room with my roommate. You have the objective that they're making that report a few years later. You have them actually provide a journal running in time around the event, and you go back and you compare the two. Turns out there's often errors there. That's not, that individual learned about it in a different way. Liz Phelps at NYU took advantage of being in New York and has actually studied individuals who were present during 9/11. And she's done some both behavioral work and some brain imaging work. The behavioral work, what she's shown is that, of course, many individuals report very vivid memories of what happened on that day. You place those individuals into the scanner, And that sense of vivid remembering, kind of like you're reliving, and it's very powerful, entails reactivation not only in the hippocampus, but also this sort of structure here sitting in front of the hippocampus called the amygdala, which is very important for affective processing and learning about the emotional sort of valence and, of experiences. The subjective experience of vivid remembering of some past emotional event was essentially entailed the reactivation of the amygdala, a reinstatement perhaps of that emotional state. And it was the degree of that reinstatement that was correlated in essence, was associated with this subjective experience of really reliving 9/11. That said, you look at the memory behavior and you look at accuracy, and there were errors, there was forgetting, intrusions, distortions, et cetera. So it's possible some of this affective reinstatement is part of what colors our subjective experience of feeling like we're reliving the past. I hope that sort of hits on it. I know it doesn't hit the chemistry point. It may well be in multiple systems in the brain. The amygdala is sort of coding for perhaps threat and reward values of things, or the threat and affective sort of associations of experiences. Okay, so I have about a half hour, 20 minutes or so for content. We can continue with Q&A as well. Let me sort of try to unpack this a little bit and tell you a little bit of what functional brain imaging has allowed us to do in terms of thinking about the neurobiology of episodic memory. This is unfortunately going to be highly condensed and just highlight a point or two. The field is rich. There's also, it's building on a rich neuroscience and psychological literature, both in terms of animal studies of memory and the brain, as well as human lesion and neuropsychological studies. The reason I sort of focus on brain imaging is it's a principal method that my lab uses, and it's also sort of transformed the field, as I mentioned at the outset. So the dominant technology in terms of imaging the human brain is magnetic resonance imaging. And you can sort of split this kind of imaging into two kinds or two classes of scans. One are scans that are, in essence, taking images of the anatomy of the structure, the anatomy of the brain in this particular case. But many of us, many in the room, may have sort of blown out a knee, and you go in and you have your knee scanned, and you're getting a sort of structural image of your knee. Well, you can also, of course, get structural images of the brain. You can measure sort of the cortical sheet where all the sort of computational neurons of the brain are sitting, the cell bodies, and you can measure the thickness, say, of a particular cortical region or brain region and relate that to changes in human behavior, such as decline in memory. You can relate measures of white matter integrity, white matter being the axons, the processes or the wires that connect up different neurons in the brain and therefore allow for this dynamic communication across different points in the brain. And work here in my colleague Brian Wandell's lab is sort of leading the charge in collecting diffusion tensor imaging measures of white matter and trying to relate this to very fundamental cognitive skills such as reading, language development, et cetera. But in addition to structural imaging, and diffusion tensor imaging is a relatively recent development in structural imaging, but structural imaging has been around for quite a while. Functional imaging came on the scene really around 1991, 1992. The very first reports were published in the literature in late 1991, showing that, in fact, if you listen to a slightly different signal using MR technology, you can read out not something about the structure of the brain, but something about the function of the brain. And the early work focused on perception. When I was a graduate student here in John Gabrielli's lab, we conducted the very first work using functional imaging to study human memory, and this was published in '95, so we're not talking that too long ago. And in the past 15 years or so, the explosion of work using functional MRI, it's hard to overstate how this has transformed the field. And so what's going on in functional MRI is instead of measuring structure, you're measuring function, meaning some correlate of neural processing, neural activity. Okay? And so you get maps such as this, where you can identify which regions of the brain are active, differentially active during the critical memory state versus some other control condition. The basics of fMRI, you take an individual, you place them into a standard scanning environment, MR system. You can probably see here there's a screen that they can see through a mirror. You roll the individual into the scanner. And while they're in there and you're measuring brain function, you're presenting them stimuli. You're having them perform different cognitive tasks. And you're mapping the relationship between the neural response, or the indirect measure of the neural response, and the cognition that you know as an experimenter you are asking them to perform because you're giving them tasks to do in the scanner. With fMRI, with functional MRI, we're not directly recording neural activity. It's an indirect measure that's, in essence, measuring changes in oxygenated hemoglobin, oxygenated blood, as it moves around the brain. And these changes are correlated with changes in neural responses or neural processing. And so what we're measuring typically is blood oxygen level dependent signal, which is, fortunately for neuroscientists, oxygenated blood has different magnetic characteristics relative to deoxygenated blood. When a region increases its activity in some way, this results in an initial dip of oxygenated hemoglobin as the oxygen is consumed, but then it results in a massive overshoot, and there's an inflow of oxygenated hemoglobin. And so there's this increase in blood oxygen levels, and this increase in blood oxygen levels, in essence, because of the differences in the magnetic properties of oxy and deoxyhemoglobin, result in increased MR signal measured a particular way. And so this is what you're doing. This is what you're seeing when you open up the New York Times and you see that commentary in the op-ed piece about your brain on politics. They're doing this. They're tracking blood flow that's correlated with neural responses and trying to infer what's going on in the brain. Okay? So on the learning end, there's been numerous strategies to try to identify the networks and the structures that are important for building new episodic experiences. We know from the lesion work that the medial temporal lobe must be important in some way. We know from animal work as well that the medial temporal lobe is important. We also know from lesion work that other structures kind of modulate learning and remembering as well. In some of our early work, we used the strategy of using functional MRI and acquiring images of the individual's brain function during individual experiences and asking the question, is there something different going on in the brain during an experience that the person will later on remember versus an experience that the person will later on forget? With the logic being that there might be some predictive information in those differential neural responses that can allow us to begin to gain some leverage on the underlying neural systems that are important for building memories. And so the strategy for these kinds of experiments is to bring somebody into the MR scanner and have them encounter a whole host of events, a long, say, list of items that are experienced one at a time. All the while we're collecting these measures, fMRI measures of neural responses to each event. Then we'll take them out of the scanner, say 20 minutes, an hour, 24 hours later. We'll give them a surprise memory test. They didn't know when they're in the scanner that we were going to be assessing their memory. Memory learning is an incidental byproduct of cognitive processing. It just happens. So they're outside of the scanner, and we give them a surprise memory test, probing their memory for the events that they encountered in the scanner. And based on these behavioral responses, we can code those events into events that were later remembered or later forgotten, and we can go back and back sort the data we collected from the brain and sort them into experiences that were remembered versus forgotten at some point in the future and ask what was the differential response. And in the first study that we used this strategy, in which we used this strategy, what we observed, what you're seeing is sort of an inflated, it kind of looks like a balloon. It's the human brain, which consists of sulci and gyri, and you kind of inflate it so that the sulci and the gyri are on the same surface, so it's a little distorted, but you can see all the cortical structures. Regions in red are regions that were more active during experiences that were going to be later remembered versus those that were later forgotten. And what immediately jumps out at you is that the frontal lobes seem to be particularly correlated with memory outcome. Okay? And the neuropsychological literature would point us to the medial temporal lobe, and that's in fact true, and we'll go over that in a moment. But the frontal lobes also seem critical. It's not that the frontal lobes are critical as the seat of memory again, but the frontal lobes are critical because they're in essence gating what's going on. The frontal lobes are biasing what's going on elsewhere in the brain, and therefore favoring particular aspects of experiences or particular experiences for being bound into memory by the medial temporal lobe. And so here in prefrontal cortex, this study, and now there's been about 150 such studies since 1998, consistently observe a positive correlation between frontal lobe activation during an experience and later remembering that experience. But in addition to the frontal lobes, again, our friend, the medial temporal lobe, is also showing this positive correlation. This includes the hippocampus as well as the cortical structures surrounding the medial temporal lobes. In other work, this is just sort of a teaser, given that time is short. This is sort of a demonstration that you can show a relationship between neural responses during an experience and later memory outcome for that experience. But this is now a tool to allow us to begin to really drill down in and try to understand the mechanisms, the systems level mechanisms that favor learning versus that result in poor learning and therefore subsequent forgetting. And I won't go through all of that literature and some of the work that we've done, but just to note that you can use this strategy to look at whether there are different substructures or subregions in particular areas that are brought online when we're encoding particular kinds of events, such as an experience encountering a face versus encoding a particular, other kinds of events, such as encoding visual spatial information about a room. And we know that, again, these different cortical regions are processing differentially these different kinds of event features. It turns out they project into the hippocampus and the medial temporal lobe at different points along the medial temporal lobe. And so we can now actually witness that using functional MRI. Here is sort of a single subject's medial temporal lobe. Here's the hippocampus up here in green. It's whipping around. And these are down here, the cortical regions that project into the hippocampus. So now three-dimensionally inflating that individual's hippocampus and medial temporal lobe. You see the hippocampus all right there. And then coming out into cortex and these cortical structures that directly project into the hippocampus. And you can see that different in this particular individual, different points in the medial temporal lobe along the anterior part versus the posterior part were differentially responsive during the learning of experiences with faces versus the learning of experiences with complex scenes. And so we can kind of use this technology to further sort of drill in and try to understand some of the systems level mechanisms. What about this point that the act of remembering is, in essence, this act of reinstating patterns that were present during the experience? Here, too, this has been actually a particularly challenging problem to try to tackle. It's been a hypothesis for quite a while. In the animal literature, there's some evidence of that, but it's very difficult actually to conduct. It's possible, but it's very challenging to conduct animal studies where you're exploring one-shot learning, which is what our episodic memories are, right? They're memories for a unique episode. And so testing this hypothesis that remembering entails the reactivation of cortical patterns that were present during learning was very difficult, both from in the animal literature as well as in the neuropsychological literature, because you don't have measures of cortical activation. All you have is an individual with a brain lesion and you have their behavior. So functional MRI has begun to allow us to address this particular hypothesis. And here's patterns of activation when the person is encountering or having an experience where there's something where they're thinking about people, they're thinking about particular famous individuals, versus they're thinking about scenes, they're thinking about particular famous landmarks in the world. And what you can see is during learning, there are different cortical structures that are differentially active, the regions in red, that are differentially active when people are having an experience where they're thinking about a famous individual in some way. Other cortical structures that are differentially active when people are thinking about spatial landmarks and sort of famous landmarks. And this kind of fits a richer literature about the processing of face information, person knowledge, as well as visual sort of object coding and landmark or spatial coding in cortex. Okay? The critical question, yes?
Is the right hemisphere or the left here represented?
Everything that I will be presenting, the right hemisphere is on the right side of the slide and the left is on the left. Thank you. Sorry, in contrast to radiological convention. Thank you. What happens now at retrieval? At retrieval, we're cueing them with words, and they're trying to bring back to mind, gee, did I think about a famous person when I encountered that word during learning, or did I think about a famous landmark when I encountered that word? And this is what we see at retrieval. What we see is patterns that in cortex that look a lot like the patterns that were present during encoding. When they're successfully retrieving and remembering that they had thought about a landmark, a spatial landmark, when they encountered this word during learning, you see these structures that were active during encoding of landmarks, active when you're retrieving that episode, even though there's nothing about the landmark in the input. It's a verbal cue to try to retrieve this episodic experience. And same with, on the flip side, other cortical regions that are reactivated when you're retrieving, having had this experience of thinking about a famous person. Developments in the last, really it's the last 7 or 8 years, but in the memory literature, as well as elsewhere, the last 3 or 4 years, in using machine learning algorithms to, in essence, carve patterns of brain activity using fMRI data, have allowed us now to go beyond these sort of coarse descriptions of similarity. And what we now are able to do is we can take the data from the individual subjects' brains as they're having these different kinds of experiences. We can feed those brain patterns into a machine learning algorithm that's, in essence, finding a hyperplane through the pattern of brain activation that splits it into the brain state when people are having experiences associated with famous people versus having experiences associated with famous sort of locations. We're training this algorithm to, in essence, classify 2 different brain states. And then what we can do is we can feed in the data collected during retrieval, and we can ask, does the retrieved pattern during retrieval look more like brain state 1, encoding state 1, versus more like encoding state 2? And it turns out we can do moderately well. We're significantly above chance in classifying, the classifiers classifying the retrieval pattern as either reflecting the encoding state 1 or encoding state 2. And moreover, what we find is that, in fact, when the subject is correct, when they thought about a famous person, and now they're remembering at retrieval they thought about a famous person, their pattern of activity, according to the classifier, their pattern of cortical activity looks more similar to the pattern that was present when they were thinking about people versus thinking about scenes, locations. By contrast, when the person has a false memory, and they actually were thinking about a famous person, but at test they said, no, I actually think I thought about a landmark when I encountered that stimulus, their pattern of activity doesn't reflect what they really did at retrieval. It reflects the other state. It's as if during retrieval, they reinstated the wrong cortical pattern. And this, we don't have the causal direction right now, but this is perhaps the evidence that they're using to lead them to erroneously claim, I had this type of an experience because you've reinstated one encoding pattern when you actually had a different type of experience. So we can begin to use functional brain imaging in conjunction with these machine learning algorithms to quantify the similarity between different brain states. Okay? And this is where I'm going to go in the remaining 5 minutes or so of my talk. Okay? So here's just some high-level sort of points about the brain and memory, or episodic memory. Building episodic memories for life events depends upon the hippocampus and the surrounding regions in the medial temporal lobe. Depends on the interaction between these regions and other cortical structures. The hippocampus binds. It's uniquely positioned to bind the elements of an event into a unique associative representation. The frontal lobes modulate memory by favoring particular aspects of experience that are relevant to our goals. Damage to the hippocampus and the surrounding structures results in a dense anterograde amnesia, which is the inability to form and therefore later remember new long-term memories of life events. And this is, again, often the first symptom in a lower grade level than what you see with extensive medial temporal lobe damage, but the first symptom in Alzheimer's disease. And the frontal lobe damage doesn't result in a dense amnesia, but it results in memory impairments indirectly by impairing goal-directed cognition and essentially this biasing of what gets acquired in memory. Remembering past events entails this reinstatement, at least partially, of brain patterns. And if we had done this with emotional states, we probably could show this correlation between the degree, be a hypothesis that would show a correlation between the degree of amygdala reactivation and the subjective sense of sort of the emotional color and intensity of that experience, memory for that experience. Okay, and again, this also entails this dynamic interplay between the medial temporal lobe and other cortical structures. Okay, let me get to, in the final few minutes, the title of the talk. all of this was hopefully interesting sort of setup, but and this is good that I don't want to, because this is ongoing work and because it perhaps is a little sensitive, I don't want to dwell too long here anyway, but let me sort of start to motivate this question. So we've acquired over the last 15 years or so considerable knowledge using brain imaging about the systems level mechanisms that support memory formation, episodic memory formation, and episodic retrieval. And this is not only advanced theory, but it's also the rapid developments in functional MRI technology, both in terms of acquiring the data itself and then using things like these machine learning algorithms to analyze the data, perhaps propelling functional MRI as a tool that might extend beyond the lab and theoretical work into society, right? And there's been a number of points of tension, or tension's not the right word, there's been a number of points of contact between functional brain imaging of different forms and different societal applications. I don't know how many people saw this article in the New York Times about this murder trial in India, in Mumbai, India. In essence, the long and short of this case is that Mumbai, India has a forensics laboratory. The forensics laboratory uses EEG technology. There's some in the room who are leaders in EEG technology more so than I, but uses EEG technology to investigate whether or not suspects in a crime, in this case it was a murder trial, suspects in a crime have experiential knowledge of the key facts of the crime. And what they mean by experiential knowledge is just not just knowledge of the facts of the crime, but brain patterns that reveal that they could only have that knowledge by having been present at that time in the crime, okay? Seems pretty far out there. There's zero empirical publications documenting this approach. None. If you read, and I have a few snippets, we'll see if we actually have time, of the judge's transcript, the judge was dramatically swayed by these brain pattern data and the forensics experts' testimony. The suspect was actually convicted of murder, not entirely, but my understanding is all the data were circumstantial, but heavily dependent upon this method. This method has been actually used in 75 cases, supposedly. And a colleague here, now a law student, Emily Murphy, here at Stanford Law, but who was part of sort of a collaborative effort supported by the MacArthur Law and Neuroscience Project with Hank Greeley, who's here at Stanford Law School. Emily had a recent trip to India and met with the lead investigator, the forensic scientist, and he believes he's doing, of course, the best thing for society and is trying to find truth. All of this work, they're basically bringing the suspect in, put him in a dark room, auditorily pipe in the facts of the crime, get patterns of brain activity at the scalp using EEG, and determining whether or not the person actually was present and committed the crime. Okay? We're not doing that in the States.
So does the person describe the scene, or do they give him views about the scene?
You're talking about how the interrogation is performed? My understanding is that the suspect was brought into the room. The suspect said nothing. The suspect sat in the room and had the auditory facts of the case piped into the room. The suspect heard the facts. There was a measure of the neural response to each of the facts. And the forensic scientists inferred from these patterns. And then I believe the same kind of machine learning pattern analysis determined that, in fact, the brain pattern showed that this individual was present during the critical acts. They had knowledge, they had memories of the experience, of these facts of the crime, and that those memories could only have been acquired by having actually participated in the event. Now, we're not doing this here in the States. It's now 7 minutes, and do you want me to stop for Q&A, or could I just go for a few more minutes? Okay. So we're not doing that here, but here's a different point of contact between neuroscience and functional brain imaging and society. There are two companies, Noli MRI and CFOS Corp, that are offering services for pay You can come in, and if your partner has accused you of having an affair, you can come in. They advertise this as one of their services. We'll ask you questions about your affair, and we can show data to your partner that, in fact, our brain scans show that you were actually telling the truth when you said you did not have that affair. Okay, that's sort of one instance. We got a phone call, Hank and others, from sort of, I don't think it was the prosecution prosecutor in San Diego, but there was, in essence, a child custody case in San Diego earlier this March. The father had been accused of molesting his daughter. He denied it, and I think he was now, my understanding, I don't know any of the details of the case. I'm talking about this just from a non sort of interested party here about the science behind it. The father, I'm understanding, was basically trying to be able to have custody of his daughter again. He hired no-lie MRI, went in and was asked questions about whether or not he had molested his daughter, and no-lie MRI generated a report based on their technology saying that, in fact, when we asked him whether or not he did X, Y, and Z with his daughter, the brain scan suggested he was telling the truth when he said no, he didn't do those things. Okay? And they wanted to enter that as evidence in this child custody case. And the lawyer representing the child, I believe was representing the child, didn't know much about functional MRI, let alone the state of the field in terms of whether you can use functional MRI to detect truth versus deception, and reached out and began to ask Hank Greeley, who has written about extensively about fMRI, sort of a lie detection technique. I spoke with him about basic functional MRI methods and things I would want if I were to look at the data from no-lie MRI. There was Mark Rakel, who had served on the National Academy of Sciences panel assessing the validity, the accuracy of standard polygraph post 9/11, because the government was very interested in whether we could sort of revisit and really begin to use polygraph more extensively. And those data are a bit challenging. The high-level point on this is right now it's not accepted standard to use these techniques. The field, the published work supporting high sensitivity and high specificity for fMRI to detect when somebody's lying versus telling the truth. I don't find it compelling. I know of many other colleagues who don't find it compelling. There are some who do find it compelling. Yet, there are efforts to try to get this into the US courts. And these efforts will continue, and at some point it may well happen. Okay? So what's critical, I don't want to prejudge whether ultimately fMRI, the data will ultimately support the use. What's critical is to begin to assess this, okay? To be able to begin to assess what can functional MRI do, how well can it do, and in what context does it perform with high sensitivity specificity, what context does it break down. And then the final 3 minutes, so Wired, in fact, I mean, this got a lot of attention, the no-lie MRI San Diego case. Wire ran a story noting that MRI, functional MRI, lie detection was finally going to have its day in court. A few days, my understanding, before the Fry hearing, which is the hearing where there's a discussion of whether functional MRI for lie detection is actually accepted practice, the team who was trying to introduce it as evidence decided to pull back, and they essentially requested that they retract this evidence from the case, and they didn't want to have the Fry hearing. It's not clear why why they sort of pulled back from having that hearing. Okay, so the long and short of where we're going, we're assessing the fMRI lie detection literature, but it's not what my lab is focused on. We're a memory lab, and so what we're trying to ask is a little more closer to the BEOS case, the India case. How well can functional MRI do in terms of detecting people's memories, individual memories? Can we, in reading out their brain patterns using these machine learning algorithms that I described, can we accurately classify whether or not a person is remembering having encountered a stimulus, say a face of a person, versus correctly saying, oh no, that's a novel person, I've not encountered them before, okay? So the very quick summary of the design, individuals are encountering, subjects are encountering individual faces. They see 200 faces during study. People's face memory is very good, so don't, but it's a lot of faces. Then we scan them while they're making memory judgments. They see the faces that they saw during study, and they see novel faces. And we ask them to indicate whether or not they recognize the face as having been encountered before, or whether they think the face is new. And we have them make other judgments, but we can kind of gloss over that for now. And the key thing is we have two kinds of trials that we're going to care about for this talk. Items that were previously encountered, so they're truly old, and the person accurately recognized or experienced that stimulus as, yeah, I've seen that person before. I recognize it as old, hits. Items that are truly new, that the person doesn't have this subjective sense of remembering having encountered the person, they're correctly rejecting that face as not having been seen. It's a new item. What we do is, the long and short of it is, we use these machine learning algorithm to train up the algorithm to discriminate, using a subset of the data, between the brain state when the person is recognizing an old item as old versus recognizing a new item as new. And we're training up this algorithm based on functional MRI data throughout the brain, just feeding in this pattern of activation for each of those experiences into the algorithm. And it's trying to find sort of playing through the pattern of brain data, functional brain space, that discriminates recognizing old items as old versus experiencing new items as new. And moreover, these algorithms, what's nice is they give you a quantitative measure. And so you can, in essence, sort trials based on whether the algorithm is confident. Here, there's a lot of evidence that this item is new, and versus very little evidence that it's old. So here you might think the classifier is probably pretty confident that this was a new, the person is experiencing this as new. Whereas here, the brain state suggests the person's experiencing it as new, but it's not so clear cut. It's less clear that the brain state reflects absence of recognition versus recognition. And so you can use this difference score as a measure of the algorithm's confidence of the person's memory state reading out from their brain data. Here is what how well our classifier can perform. Here are the 16 subjects that we scanned. Taking all of the trials, on average, the classifier is 77% correct, being able to discriminate true recognition from true non-recognition, correct rejections. Now you might say, well, that's not, that's okay, that's not bad, but what if we restrict our consideration of the classifier's performance to when the classifier is really accurate? Maybe you only want to bet, you only want to use the technology if the classifier is very confident. You might want to only use this under situations where there's a lot of evidence coming out of the classifier that it has high confidence in its response. So you go systematically, so these are all trials, you go to increasingly more and more confident states of the classifier, and on average across 16 subjects, the classifier can discriminate recognizing something as old versus experiencing something as new, on average about 94%, which is pretty high sort of performance, right? A bit higher than I would have thought, and one could imagine sort of looking at these data and saying, fMRI may well be ready for prime time to detect different memory states. And this will be my last slide, because I think for time reasons, I'm actually 2 minutes over. I hope I'm not making you late for your next class. There's a whole host of caveats. The most important caveat is, I saw a number of heads shaking when I emphasized the point about the BEOS technology being a claim about where the knowledge came from. The claim that the knowledge came from having been present for the experience. We know from other brain imaging data that false recognition, and it's something that's similar to some past event, can result in cortical reinstatement and brain patterns that look a lot like the pattern of a true event. So you could, in essence, have a neural signature of that suggests true recognition that really is false retrieval. And I kind of showed you a hint of that already. In addition, what these data show is that you can discriminate whether or not a person is remembering having seen some stimulus versus experiencing something as new in highly controlled situations. Very simplified, non-complex experiences. Single faces where the person's thinking about the face. What about complex real-world experiences where the person's attention is divided, et cetera? Third, what's critical in terms of memory for most uses in life is to know the source, for many instances in life, is to know the source of our knowledge. And in fact, that's the critical claim in the BEOS case. The judge, in fact, writes, and I'm going to skip one point to get there, the judge, in fact, writes about how the knowledge that the defendant demonstrated is experiential knowledge, that the individual could not have experienced it. I think it's on this slide. I'll just do it in words. Could not have come to this knowledge by hearing about the facts of the crime on the local news. Could not have come to this knowledge by reading about it in the newspaper and hearing about it on the radio. Could not have come to this knowledge by, upon hearing about it on the radio or reading the newspaper, imagining, gee, what might have happened during this crime, and imagining the experience. What we know is that retrieval patterns of episodes look a lot like imagination of experience. So the ability that we've shown to differentiate whether somebody is simply recognizing a face of having been seen before or experiencing a face as novel is a far cry. That ability to discriminate that is a far cry from what we want to be able to do, which is to say, not only is this person perceiving this face as familiar, but the reason they're perceiving that face as familiar is because the source of that knowledge is they were present at some incident where that person was also present. And that discrimination of the source of our memories is going to be a lot harder to crack than the simple thing we've done here. We're going to do, my lab, and I imagine other labs, will do the basic cognitive neuroscience to assess how well these technologies might actually perform under those situations. It's hard for me to imagine it's going to be at the level we're talking about here. And so I'm going to leave you with both the promise of these techniques. This is just sort of a summary slide of many of the caveats. You can do this classification under very highly controlled, non-realistic situations. There's no published data showing that fMRI or EEG can detect these different memory states for real-world experiences, and in particular, no data to show that you can discriminate different sources. I'm going to leave you both with the cautionary note that when you see these kinds of data out there, you should just sort of ask, what's the lay of the land? If you see in the New York Times, this is your brain on politics, Hillary Clinton is going to have a hard time in this election because she's eliciting this emotional reaction. Ask about what kind of data are supporting those claims. We wrote a sort of counter letter to the editor for those who saw that opinion piece, basically pushing back on that because there's a lot of assumptions underlying those claims from the brain patterns. Similarly, our society this isn't going to stop. Society is going to be moving forward in this goal of trying to use these technology in other settings. There's pressure to try to do that. And we need to critically assess what the technology can and cannot do. We'll see where the data fall. And then finally, sort of leave on a positive note. Here's Jane Austen basically saying, the ability to sort of gain leverage on and understand our memory, I'm not optimistic there. It's a particularly challenging cognitive set of cognitive abilities, and it may be very difficult to gain leverage on those systems. I hope what I've shown you is both in terms of the psychology as well as the neuroscience, we're gaining a lot of leverage on these systems, and I think the decades to come will obviously, or hopefully, continue to unravel the mysteries of memory, both in terms of our mind, but also in terms of the brain bases of different forms of memory. So thank you for your attention.
It was shown in Hippocampus studies that recognizing the face is a right brain function. And we've seen that in being able, in the functional MRI, we've seen that in your facial recognition work that more activity is in the right side of hippocampus.
So it's a great question. So the question is sort of material or content laterality effects. And in fact, using that subsequent memory paradigm as well as that looking at the data during learning sorted by later memory outcome. We and others have actually shown that you can get laterality effects in the frontal lobes as well as in the medial temporal lobes for different kinds of content. Verbalizable, and semantic experiences tend to be left lateralized. It's not a strict lateralization, but it's biased towards the left. Faces that are non-famous often can be right lateralized initially, And some work by Bill Kelly at Dartmouth has shown that you have unfamiliar faces where you're less likely to be able to label them. It's often right lateralized. You have familiar faces, and you get bilateral activation as if you have both attention to and representation of visual object form that might be slightly right lateralized in terms of frontal attention mechanisms, and then linguistic coding via the left hemisphere. Yes.
First, thank you for a lovely lecture.
Thank you.
For those of us who are interested in this topic, Greeley is speaking at 3:30 this afternoon in the law school Alumni.
Please do catch Hank. Hank, in fact, has, if you're interested in this, especially about neuroscience technology in society, including in the courtroom, Hank has written some really, some of the leading work in terms of thinking about the sort of the ethical challenges that come up there, as well as just what's the state of the science right now, and is it premature or is it ready to roll?
For more, please visit us at stanford.edu.